paramagnetism. So there's an equation for bond order. Okay, bond order is half times the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. Okay, and a bond order is literally a number which tells you how many electrons are being shared in the bond. So a bond order of 1 is a single bond, a bond order of 2 is a double bond, a bond order of 3 is a triple bond. If the bond order is 0, that's telling you there's no bond. Okay, so bond order equals 0 is what we call unstable. Okay, so look out for that. Diamagnetic versus paramagnetic. Diamagnetic means there are no unpaired electrons. So diamagnetic equals no unpaired electrons, which means it's repelled by an applied magnetic field. Paramagnetic means one or more unpaired electron. Okay, you can have one, a little bit paramagnetic, more paramagnetic. So if you see any unpaired electrons, it's paramagnetic. So it's attracted to an applied magnetic field. So it's very binary. It's either diamagnetic or paramagnetic if it's got none versus one or more unpaired electrons. So let's start with picking on fluorine. Although I wouldn't pick on fluorine in a fight because I'd probably lose. So fluorine, write the electronic configuration of fluorine. It'd be 1s2, 2s2, 2p5. And if you want, you could put those actually in your atomic orbitals just so you can see which electrons are being confined. So 1s2, 2s2, and remember you've got to use the group 16 or above, 2p1, 2, 3, 4, 5. Okay, so we got 2 of those, right? So again, I could fill in my other atomic orbitals like so. And then I've got to work out how many electrons I've got to put in my molecular orbitals. Okay, so it's fluorine 2 plus. So F2 to start with would be, hang on, I didn't add up how many electrons I got. 2 plus 2 plus 5 is going to be 9 electrons. Sorry, I thought I said that already. So F2 is going to be 2 times 9 electrons, so that's going to be 18 electrons. However, this is F2 plus, so F2 plus has lost an electron. So we're going to have to subtract 1 off there. So that's going to have 17 electrons that we are going to have to put in our molecular orbitals. Okay, so I'm going to start from the bottom according to the Aufbau principle. If I have to pair up, I'm going to use the Pauli exclusion principle that they have opposite spins. And if I reach any degenerate orbitals, well, then I have to singly occupy them before pairing up according to Hund's rule. So 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so I've got 3 electrons in my pi star 2p. Okay, so is it stable? Well, to work that out, I've got to work out the bond order. So it's going to be half times my number of electrons in bonding orbitals. So those are the ones without the asterisk. So 2, 4, 6, 8, 10 electrons in bonding orbitals, minus the ones in anti-bonding orbitals. So 2, 4, 6, 7. 10 minus 7 is 3. 3 divided by 2 is 1.5, right? 1.5. So my bond order is 1.5. So that's like telling me there's a resonance between a single bond and a double bond. Okay, if it's not 0, it's stable. So I can say it's stable. Yes. Is it diamagnetic or paramagnetic? I have 1 unpaired electron in my pi star 2p. That makes it paramagnetic, and my bond order is 1.5. So just as an FYI, remember this is the valence versus core electrons again. So you could only do this with the valence electrons if you choose. I've been showing the core because that's what's on my diagram, but you would get the same answer if you ignored the core electrons. So for example, with the bond order, it'd be half, and then the number of electrons in bonding orbitals, 2, 4, 6, 8, minus the number in anti-bonding orbitals, 2, 4, 5. 8 minus 5 is 3. 3 divided by 2 is also 1.5. Okay, so that's just a quick check in case you are ignoring core electrons, which I'm totally cool with. Okay, so I'm going to ignore the O2. You guys can do that. And I'm going to do the carbon example so we can use my other other side. So I'm going to carbon to minus. Okay, so first of all, carbon electronic configuration 1s2, 2s2, 2 p2. Okay, so that's a total of 6 electrons. So if we have carbon 2, dicarbon, that'd be 6 plus 6 would be 12 electrons. We have C2 minus, so it's gained an electron. So we're going to have to add 1, so it's 13 electrons that we're going to put in our molecular orbitals. We're going to use the diagram on the left for the group 15 or below. All right, so if you wanted to, you could put in your atomic orbital electron configurations for the carbon, or you can just go straight in if you know how many what do you call it? Oh my goodness. How many electrons you're dealing with, right? So we've got to do 13. So let's start at the bottom and work our way up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Singly occupying the pi 2p. 11, 12, and then 13. 1 billion ohms. Electron sigma 2p. So the bond order then is bonding orbitals, that's the one without a sigma asterisk. So 2, 4, 6, 8, 9 electrons in bonding orbitals minus 2 electrons in anti-bonding orbitals minus 4. 5 divided by 2 is 2. So we have a resonance somewhere between a double bond and a quadruple. So again, it's not 0. So that means that we are stable. Is it diamagnetic or paramagnetic? We have got a measly unpaired electron in the sigma 2p, so that would be paramagnetic, okay? And the bond order we calculated was 2.5. Just as an FYI, if it was, I don't know, to make it easier, if it was C2 2 minus, okay, so this is entirely hypothetical, C2 2 minus, that would have gained 2 electrons and would have 14 electrons, okay? So then we'd have another spin down electron, and that would be what something that's diamagnetic would look like, that the electrons were paired. Okay, so I hope that was helpful for you.